Welcome back. Let's look at section 3.3. We're going to be doing division with polynomials. We have two different ways to divide. We are going to talk about first long division and then synthetic division. Long division you know how to do, or at least you knew how to do it one time. That's the meaning of that. Cast your mind way back here at the beginning. How do you do long division without a calculator? Most of us probably learned to do long division in maybe 4th grade. But typically this is something that we just kind of pull out our calculator and plug it in to do. So let's start here with some vocabulary for division, so that when we talk about our division problems, you're going to know which number I'm referring to. We start with a dividend, and it goes underneath that doghouse division sign, our dividend, D-I-V-I-D-E-N-D. Our dividend is divided by the divisor. The thing that divises is the divisor. And the answer to our division problem is a quotient. Now, typically we do division problems as a fraction in algebra, and when we do division problems as a fraction, that dividend is what we are dividing, goes on top in our numerator. Our divisor is our denominator, it's what we are dividing by, and our quotient again is the answer. So there's our vocabulary for division. Let's do a division problem, a long division problem, just with numbers, so that we practice and we remind ourselves of the steps that we go through. Now I picked something kind of crazy that wasn't going to go nice and even, so get that written into your division symbol. Notice that it ends in a 6, which that's when I said it's not going to go evenly. Since I'm dividing by 5, my divisor is 5. The only way it's going to go evenly is if it ends in a 5 or a 0, and this doesn't. So I know I'm going to have decimals or a fraction as a remainder. Okay, so when I start doing my division, I ask myself the question, how many times does 5 go into 2? Well, it doesn't, so I move over and I include that next digit. How many times does 5 go into 23? Well, 5 times 4 is 20, so it will go 4 times. Now notice that I asked myself the question, how many times does it go? And then I put that answer up in my quotient line, and the next step was to multiply. 4 times 5, my quotient number times the divisor, and then I write that product down. The next thing I will do is subtract. 23 minus 20 is 3, and then we bring down that next number. Alright, I ask my question again. I go back to that same question. How many times will 5 go into 37? Well, 5 times 7 is 35, so it will go 7 times. I write that number in my quotient line. Notice that I'm keeping my columns nice and straight, so I know where I am in the problem. After I write a number in my quotient line, I multiply. 7 times 5 is 35. I write down that product and I subtract. Step by step, same thing every time. Then I bring down my next number. Ask my question again. How many times does 5 go into 21? Well, we already saw that 5 times 4 is 20. So keeping my numbers lined up, this stuff is important. Make sure that the things I'm saying you are doing. 4 times 5 is 20. Write that product down and subtract. Over and over and over, I'm just repeating that same process, working my way through the problem. Now, I get down here, oh no, we're still good. How many times does 5 go into 12? It goes 2 times. Everything's lined up. 2 times 5, do my multiplication, is 10. I've got a 2, and I bring down my last number. How many times does 5 go into 26? Well, 5 times 5 is 25. 5 times 5 is 25, and it doesn't go evenly. I've got this 1 down here. What do I do with the 1? Well, I've got options. I could add decimal 0 and decimal 0, and then I would go again, and I can divide that out as a decimal. or I can write it as a fraction, and that's the option we are going to choose because that's what we're going to use with our polynomial long division. We're going to take this remainder, we're going to bring it up to our quotient line and place it over the 5 because that's what we have left is 1 out of 5. 5 is our divisor, our remainder goes over our divisor. So 237,126 divided by 5 is equal to 47,425 and 1/5, or that would have been a decimal 0.2 if we'd gone with decimals. We've got our dividend, our divisor, and our quotient. Okay, that's our long division process. Kept asking the same question, write something down, multiply, subtract, ask the question, write something down, multiply, subtract, working through, same process over and over and over. Well, how is this going to help us with graphing polynomials? That's the question, right? It's going to help us with graphing polynomials because this is going to allow us to find points on the graph. How about 2? This allows us to find points on the graph. Now we have a lot of theorems. We have a lot of theorems in our unit this time. Here's another one. We've got our remainder theorem. Remember, we're learning our mathematical language. We're putting into words the structure of what we are doing when we are doing our algebra. The remainder theorem tells us that if r, some value r, is the remainder. What's a remainder? Well, right there, that was a remainder, that leftover bit that didn't go evenly. If r is the remainder when some polynomial function, and I'm just going to name it p of x for polynomial function, when I have a polynomial function divided by an expression, and the expression we're going to define is x minus c, so x minus some number, then the remainder is the function value at c. The remainder is the value of the function at c. So I plug in, basically, I plug in a number for x, my remainder is y. So I can think of a point on the graph, I plug in c, and I get that remainder as my function value. Alright, now, you know, depending on the shape of our graph, we've got an infinite number of points, right? We have a continuous curve for our polynomial functions. Let's think about how we use this. What points in the graph are we primarily interested in? As we're graphing these functions, we are mostly interested in those x-intercepts. It's what we call zeros or roots of the function. Those are the points we're primarily interested in. Where does our function hit the x-axis? Now, if I'm on the x-axis, let's think about this. If I'm primarily interested in, no matter what, whatever the shape of my graph is, if I'm primarily interested in these x-intercepts, what will the remainder be? Now, keep in mind, the remainder is my function value. My function value is the same thing as the y value. What's my remainder at these points? Well, they're on the x-axis, so the remainder, the function value, is going to be 0 because that's my y value when I'm on the x-axis. Okay, so we're going to be using our remainder theorem to help us find these zeros for our function, these x-intercepts, where my y value, my remainder, is 0. So keep that in the back of your mind. Let's look at that next page. Now remember I told you we've got two types of division. We've got long division and we've got synthetic division. So our first type of division is long division. Our second type of division is synthetic division. I'm going to tell you right now, you're going to like synthetic division better. But there are some cases where you have to use long division. So we gotta practice long division. You have to know how to do it. Long division, when you have the divisor in your polynomial long division, okay, divisor. Divisor is the number you're dividing by. The divisor in polynomial long division is our expression that we were just talking about, x minus c. Okay? So we're dividing by an expression, not just a single value like we did here. Our goal is to determine if the expression represents, what are we looking for? It represents the expression would represent a factor, because a factor gives us a root or a 0 or an x-intercept for our function. If our expression we're dividing by is a factor of our polynomial, then the remainder is 0 and we found a root. Okay. Something you have to remember is that every term must be represented. Use 0 placeholders if we need to. What does that mean? Every term represented means when I look at my exponents, I count down from whatever that largest exponent is and nothing is left out. Like right here, my largest exponent is 3, so I've got 3, 2, 1, and this would be x to the 0 power. 3, 2, 1, 0, or 3, 2, 1 constant. Every term is represented. I don't need a placeholder. We are finding the value p of 3, but I know that if I'm doing long division, I've got to turn that into an expression. So p of 3 means x equals 3. That's what I've plugged in for x. But I'm backing this up and turning it into an expression. So I need to move that across to the other side of the equation. So my expression would be x minus 3. That's my expression. That's what I need to divide by with long division. With synthetic division, you can just use 3. But with long division, you need to take that value for x and you need to turn it into an expression. All right, so that's my divisor. The polynomial is my dividend. So let's set it up. We've got our dividend. Every term is represented. You have to keep this organized and straight vertically. So give yourself space, write it neatly. Make sure that you're following my instructions. If you get everything all messed up and try to squish it in, you're going to end up in a mess and you're going to miss steps. So make sure that you're following through. Okay, so just like with our regular long division, we ask ourselves a question. The question here has to be a little different though, because I have this expression over here, not just a single value. So my question is going to be, what would I have to multiply by x to get 2x cubed? What would I have to multiply by x to end up with 2x cubed? And I'm just going to show you over here, x times something equals 2x cubed. Well, I would have to multiply by 2. I've got 1x, I need 3, so I would have to multiply by 2x squared. X times 2x squared gives me 2x cubed. So this is what I have to multiply by. That goes in my quotient line. And it needs to line up with my squared column. So I'm going to put 2x squared into my quotient line in my squared column. So I wrote something in my quotient line. The next step, just like with regular long division, is going to be to multiply. Now when I multiply over here to my divisor, I've got two things to multiply it to. 2x squared times x is 2x cubed. That should always match. That's my goal. The next one says 2x squared times negative 3. Well, 2x squared times negative 3 is a negative 6x squared. After I've multiplied, what did I do with my long division? I wrote something down, I multiplied, and then I subtracted. So that's what we do here. We wrote something down, we multiply, and now we subtract both of those terms. Now this bit's important. My parentheses are important because I'm subtracting both of those. It changes the sign on both of those. That negative distributes inside and that changes to a plus here. Now my goal was to cancel out this first term and that worked. 2x cubed and negative 2x cubed, those add to 0. Now I see what I've got here. I've got a negative 5 and a positive 6. That leaves me with a positive x squared. And instead of just bringing down the next single term, I'm going to bring down the rest of the problem. All right, we went through one cycle. Let's cycle through again. We ask our question. What times x gives me x squared? Well, x times x gives me x squared. So I put that in my quotient line, positive x, because this is a positive x squared, so it's plus x, in my x column. Keep it lined up as well as you can. I've got something in my quotient line, now I multiply. X times x is x squared, that should always match. X times negative 3, don't forget that bit. And then after I've multiplied, I subtract, because that's my process. All right, when you subtract, you are distributing that negative to both of those terms, so it changes the sign on both of those terms. So I have a negative x squared, those should always add to 0, that was my goal. 4x, and that became a positive 3x, so that's 7x, and then I bring down my minus 6. Cycle back through, ask myself the question again. What times x gives me 7x? Well, that's a positive 7, because I need a positive 7x. After I've figured that out, put something in my quotient line, I multiply. 7 times x is 7x. Then don't forget this bit, 7 times negative 3 is negative 21. Now that I have that down, I subtract both terms, which means I change both signs. That negative multiplies in, changes the sign on both of those terms, and I'm left with, that's going to add to 0, always should. Negative 6 and positive 21 gives me a positive 15 as a remainder. It did not go evenly, which is fine. Now, how did we interpret our remainder with regular long division? We took our remainder up and we put it over our divisor. Now, we don't have any signs here, plus or minus, because this is a single term with a bunch of digits. So it is all the same sign. It's not separated out. Here we're doing plus and minuses. This is a positive 15, so when I bring that up to my quotient line, I do plus 15 over my divisor. All right, excellent. Now what does this mean for us? Remember I told you that our remainder theorem says the remainder is the function value at that value c. So we have a point on the graph. Whatever c was compares up with that remainder. I was dividing by 3. I got a remainder of 15. That's a point on my graph. Is that point on my graph on the y-axis? Well, no, it's not, because my remainder was not 0. So it's not a 0 of the function, which means that expression x minus 3 is not a factor. Okay, so those are things that we know from doing the long division. Right now we're really just learning how to do the long division. Let's do this one a little bit more quickly, but we are still going to work through the same things. We're dividing by f of 4, finding f of 4, but we're going to do long division, so we have to take that value f of 4, we have to turn it into an expression. This means I plugged in 4 for x, which gives me the expression x minus 4. That's going to be the expression that is my divisor. So let's set up our problem. X minus 4 is our divisor. Our dividend is this polynomial function here. Ooh, don't forget that we've got to make sure that every term must be represented. We're going to have to use 0 placeholders down here. We've got some missing terms. We go 4 to 2, 1, and then we don't have a constant. So we need a placeholder here, and we need a placeholder there. So when I write my dividend out, I've got 4x to the 4th plus a 0 placeholder for my cubed column, minus 4x squared plus 6x, and then plus a 0 for my constant column. So I stuck in my 0 placeholders. Alright, let's work through our process. I'm going to do it a little more quickly this time. If you need to, stop the video, go back, rewatch the first problem, come back and see what we got. Okay, what times x gives me 4x to the fourth? Well, that is going to be 4x cubed. That's why I had to have that column, that 0 placeholder. 4x cubed times x is 4x to the fourth. That matched. That was my goal. Don't forget to multiply by the -4. So that is a -16x cubed. And I subtract to move on. When I subtract, that negative multiplies in and changes those signs. That first term should always cancel. That leaves me with a positive 16x cubed, and I bring down the rest of the problem. It's easier for me to just bring it all down every time. All right, we ask our question again. What times x gives me 16x cubed? Well, that's positive, so that's going to be a positive 16x squared. Keep it in my squared column. When I multiply, that's my 16x cubed that matches. That was my goal. 16 times -4, grab your calculator if you need to. And then I subtract again. When I subtract, parentheses matter. I have to distribute that negative inside, changes the sign on both of those. That makes that add to 0. -4 and positive 64 gives me a positive 60x squared, and I bring down the rest of my problem. Cycle through again. What times x gives me 60x squared? Well, that's going to be a positive 60x. It's not always going to be plus up here. I'll tell you that right now. Sometimes you're going to have negatives, so pay attention to the sign. 60x times x gives me that 60x squared. That matches. 60 times a -4 is a -240x. Next, I subtract again, cycling through. Distribute your negative, changes the signs. That first term should always add to 0. Positive 6 and a positive 240 is a positive 246x. Bring down that 0 placeholder to remind myself I've got one more column to go. What times x gives me 246x? Well, that's going to be a plus 246. 246 times x. 246 times a -4 is a -984. If you aren't paying attention to parentheses here, even if you got to the right value, you would end up with the wrong sign. That negative distributing through makes the remainder a positive 984. Bring that up to my quotient line. So I ran out of space, plus 984 over that divisor, over x minus 4, which means that at value 4, where x is 4, my y value is 984. That is a point on my graph. Is it super helpful? No, it's not. X minus c, that x minus 4 is not a factor. So I didn't find what I was after. I didn't have a remainder of 0, but I practiced long division. Now here is an example of why we have to know long division and can't just go straight to synthetic division. I've got my polynomial divided by an expression that is not a single value of x. I've got an x squared there. Alright, so when I set this one up, you can't do this with synthetic division, by the way. You can't divide by an x squared, but you can with long division. Alright, when I set this up, I've got to make sure, do I have every term represented? I do not. I need a placeholder right there. I'm missing my squared term. So I need to do 2x to the fourth plus 3x cubed plus 0x squared, there's my placeholder, minus 7x minus 10. Alright, I've got my dividend divided by my divisor, and I need to pay attention to what it is that I'm asking here. What times x squared gives me 2x to the fourth? What times x squared gives me 2x to the fourth? Well, I'm missing a 2, and I'm missing 2 plus 2 is 4. I'm missing x squared. So 2x squared, I get to jump over to this column. Good thing I remembered my placeholder. Placeholders are going to be essential in synthetic division. Okay, multiply. 2x squared times x squared is 2x to the fourth. 2x squared times 2x is a negative 4x cubed. I need to subtract next. That adds to 0, that multiplies in and becomes positive, so I've got 7x cubed, and I need to bring down the rest of my problem. And then I ask my question again. What times x squared gives me 7x cubed? Well, that's going to be a positive 7x. 7x times x squared is 7x cubed. That will add to 0. 7x times negative 2x is a negative 14x squared. Subtract both of these. That makes this first one add to 0, and this becomes a positive 14x squared. Bring down the rest of my problem. Cycle through again. What times x squared gives me 14x squared? Well, that's going to be a positive 14. 14x squared, and then I multiply again. 14 times negative 2x is a negative 28x, and I subtract. That's going to add to 0. This becomes a positive 28. Positive 28 and negative 7 is a positive 21x, and then I've got to bring down this negative 10. Now, my remainder part down here has a lower degree than my divisor, so I'm done. I can't do anything else. I've got to take what I've got here as my remainder back up to the top. This first term is positive, so I'm going to say plus 21x minus 10 over my divisor, x squared minus 2x. There's nothing else I can do there. So this quotient and remainder is my solution. Because this is still x squared in my denominator and I've still got an x there, doesn't give me a nice pretty point on my graph. But I did try to divide out 2 degrees of the problem. Wasn't successful. That was not a factor. Okay, but it worked. I mean, like, we did what we did. It was fine. This works. It didn't advance us if we were trying to factor out this polynomial. It wouldn't have advanced us anywhere. But this is a thing that we can't do with synthetic division. Our second type of division. Our first type was long division. Now we're doing synthetic division. You're going to like this one. An alternate method for dividing polynomials. Synthetic division uses only the coefficients. We're working with just the coefficients when we're working through the division part of the problem. Instead of finding that expression, x minus c, the divisor is just the x value c. We're just dividing by c, not the expression. You have to have every term represented. That's the same as with long division, so we have to use 0 placeholders if we need them. And we can only divide out a single degree. So that problem we just did, you cannot do with synthetic division. You would have to do this problem by long division. You don't have an option. Okay, synthetic division. Now, we are going to work through, and if you look, this problem is the same problem we did with long division on that last page. We're finding P of 3 for the same polynomial. Now, we know our answer because we know we ended up with a remainder of 15. But I'm going to show you how to work through that process with synthetic division instead of long division. You're going to like it. So we don't need any 0 placeholders. We have all of our values represented. We don't need to find an expression. Our divisor is going to be that value 3. When I set up my synthetic division, I set up my division sign upside down. Now my synthetic division structure looks a little bit different than my MATLAB's. Neither one of us is wrong, but if you go through the showing example in my MATLAB, it's going to look a little bit different from what I'm doing. Same process, just the structure is a little different. Now, when I record my polynomial, I'm only using the coefficients. So 2x cubed is represented by 2, minus 5x squared is represented by a negative 5, Plus 4x is represented by a 4. Minus 6 is represented by a negative 6. I divide by, my divisor is the value x, not the expression. So x equals 3, that's my divisor. I don't have to turn it into an expression. Alright, here's my structure. This last one, the constant row, is always going to give me my remainder, so I usually block that off to make note of that. This is what you do. You bring down your first term all the way down to the bottom. I multiply on the outside. 3 times 2 is 6. I add on the inside. Negative 5 plus 6 is 1. I multiply that by my divisor on the outside, just like I would multiply what was in my quotient line by my divisor here. Multiply that quotient line by my divisor here. Add on the inside. 4 and 3 is 7. Multiply on the outside. 7 times 3 is 21. Add on the inside. 21 minus 6 is 15. Now, what we have done is divided out a single degree. So when I go to interpret my quotient, when I go to interpret this quotient line, my original problem was cubed, third degree. My quotient is 1 less. So my quotient is going to be squared. So when I interpret this quotient line, this is a 2x squared plus 1x plus 7 as a constant, and then there's my remainder. 15 would be over the expression, so I've got to think about putting that into the expression. It would be x minus 3. There's my quotient with remainder interpreted, and if you look back at that previous page, that's exactly what we got using long division. So synthetic division and long division yields us with the same results, with a little less work. It's a little bit more succinct than long division. Okay, let's go again. Once again, this is a problem you've already done. We did find f of 4 for this polynomial function with long division. So we know our answer. We know what solution we should get. Let's figure out if we can get there with synthetic division. There's our divisor. We need placeholders. Two placeholders. So let's set it up. Our divisor is that positive value of 4. Our polynomial line, just the coefficients. Placeholder for the cube term. That's essential. It will be wrong if you don't remember your placeholders. Then I've got my squared column, my x to the first column, and my constant column. You have to include those 0 placeholders. I know that I'm dividing out a single degree of x, so this 0 constant column is going to become my remainder. Here we go. Bring down the first value. Multiply on the outside. Add on the inside. Multiply on the outside times the divisor. Add on the inside. Multiply on the outside times the divisor. Add on the inside. When I multiply on the outside times that divisor again, I get that value 984. 984 plus 0 is just 984, and that's my remainder just like it was before. So I'm going to take this quotient line, interpret it, starting with 1 degree less than the original polynomial. This is 4th degree because that exponent is a 4, which means that when I interpret my quotient, I start 1 degree less, I'm going to start cubed. So that's going to be 4x cubed plus 16x squared plus 60x plus 246 is my constant, and then my remainder, positive 984, goes over that as an expression. So my expression here would be x minus 4. There's my quotient with remainder. Told you synthetic division is a lot easier. Okay, let's do one more example of synthetic division, and then we are going to talk about putting things together with a couple more theorems, how we're going to use this. Alright, do I need placeholders here? I do. I need one placeholder. I'm going to divide using synthetic division, so my expression would be x plus 2. If I take x plus 2 and set it equal to 0, that means my value that I'm dividing by is a negative 2. So I set up my synthetic division, dividing by a negative 2. I've got a 1. I need a placeholder. Negative 7 and negative 6. That negative 6 is going to be over my remainder. So let's do this. Let's bring down that first term, multiply on the outside, add on the inside. And we got a 0 as our remainder. So that's helpful. Here we go. Let's interpret our quotient. What's our first term for our quotient going to be? Well, this is 3rd degree. So it's going to be 1 less degree, which makes this 1x squared minus 2x minus 3. My remainder is 0. Go back to my remainder theorem. If my remainder is 0, then I found a factor. That expression gives me a factor. I found a factor. So let's think about this. If I had this factor x plus 2, and now I have this quotient. So I've got x plus 2 as a factor, and now I have this quotient x squared minus 2x minus 3 as a factor. This is quadratic, and I can finish factoring it out. So I've got x plus 2, and I can break this apart. My signs are going to be different because that 3 is negative, so I'm going to have a plus and a minus. 3 is prime, so it's got to be 3 and 1. I need the larger value to be negative, so I'm going to do a minus 3 and a positive 1. And I have managed to completely factor our polynomial expression. I completely factored it because I found a remainder of 0 that tells me that my divisor was a factor. That's what we're doing this for. That's why we're doing our division. Factor theorem. Here we go. This is one of those important theorems that I told you we're going to have. The number c is a 0 or a root or an x-intercept of my polynomial function if and only if that expression x minus c is a factor of the function. We're using it with the remainder theorem like I just said. If the remainder is 0, then c is a root of the function and x minus c is a factor of my function, and I've moved forward. This allows us to use our synthetic division to completely factor and graph polynomial functions that have a greater degree than what we know how to factor otherwise. Alright, we're going to do an example of everything. This video has gotten longer than I wanted it to be, but we're just going to keep going and power through. I'll talk kind of quickly through this. You may need to slow it down, go back, pause it. We want to factor this polynomial. It is a 3rd degree. Now, like I said, when we factor, our quotient is 1 less degree. So if I've got 3rd degree polynomial, my quotient with synthetic division gives me a squared expression, and I can factor that out by using reverse FOIL. So what I need to do is find one root using synthetic division. Alright, I'm going to need a 0 placeholder here. My expression is x plus 4. That's my expression. So my value is going to be negative 4 because I think about setting that equal to 0 and finding the value for x. X plus 4 equals 0, so x is negative 4, and that's what I'm going to divide by with synthetic division. So I'm going to divide by negative 4. Remember your placeholders, 0x squared, and then a 0 at the end. So I've got 1x cubed, 0x squared, negative 13x, 12. Oh, I don't have a placeholder at the end. Sorry, that's a constant. It's still early while I'm doing this. Alright. Steps for synthetic division: bring down that first number. Multiply on the outside, add on the inside. Again, pause the video. Work it on your own. See if yours matches mine. When we get a remainder of 0, we have found a factor. So I need to interpret my quotient. My original was third degree. This quotient is going to be squared. I found that this is a factor, so that's x plus 4 times my quotient. So x plus 4 is my first factor. I can factor out this quadratic. It's positive, so it's going to be both the same, but it's not going to be both plus. It's going to be both minus, because that sign in the middle is negative. 3 is still prime, so minus 3 minus 1. So there is my polynomial function completely factored. Let's graph it. Do our 0 factor chart. We know we've got zeros, multiplicity, behavior. Take each of those and set it equal to 0. That would give me a negative 4, just like I divided out there. That gives me a positive 3 and a positive 1. The exponent on each of those factors is understood to be 1, so that's the multiplicity. 1 is an odd number, so the behavior at each of those zeros or roots is that it's going to cross the graph. I know I need to count out to 4 to negative 4, so let's go negative 4. We're going to mark negative 4. We're going to mark positive 3, 1, 2, 3, and positive 1. That's where we're going to cross the x-axis. What about this y-axis? Well, my y-intercept happens where x is 0. 0, 0, I have a y-intercept at 12. Which this time, that's not crazy, right? I can think about 12 being an achievable place to put on my graph. Okay, well, how do I know where to start? End behavior. So end behavior comes from that leading term. Leading term is positive x cubed. So 3 is odd, which means one end goes up, one end goes down, and it's positive, so it's increasing. It starts low, finishes high. So I'm going to start down here. I'm going to come up, cross, 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 and there is my polynomial function graphed. Alright, let's move to the next one. Last page of notes. Deep breath, take a break if you need a break. 2 more theorems, and then we'll do 1 more graph, and we're done for today. Again, I apologize that this is longer than I intended. Fundamental theorem of algebra. If y is some function, polynomial function, oh, that's part of my definition, sorry, polynomial function of positive degree, our polynomial function, our exponents have to be positive integers, it has at least 1 0 in the set of complex numbers. Now, complex numbers can be real or imaginary. So I might not actually have any x-intercepts that show up on my graph because they could be imaginary. Our in-root theorem tells me if I have this polynomial equation, p of x equals 0, And with real or complex coefficients, real or complex coefficients, so the coefficients in front of the variable terms can be real numbers or imaginary numbers, and a positive degree n, this is the important part, positive degree n, then when I consider multiplicity, when multiplicity is considered, that function has n roots. So whatever that degree of my function is, that's how many total numbers of roots I have. The total number of roots is the same as the degree, but just notice that that includes imaginary roots. Doesn't say that they are all unique. You have to consider multiplicity. Some are repeated. So I might, if it's degree 5, I may not have 5 different x-intercepts. If I add up the multiplicity at the x-intercepts, that multiplicity will add to 5. All right, one last graph and then we're done for today. Solve and graph the polynomial function. All right, so right here, leading term. We're in order, so that is my leading term. Leading term is 2x cubed. It has a coefficient, a variable, and an exponent. That exponent gives me my degree. The degree tells me how many total times I can have a hill and a valley, a turn. It's always one less. So I can turn up to 2 times, 1 or 2 times. My in-root theory tells me that I can expect the number of roots to be the same as the degree, but they may not all be different. They may not all be real. They could be imaginary. Y-intercept happens where x is 0. So if x is 0, x is 0, x is 0, my y-intercept value is 2. Oh, that's lovely. That shows up nicely on my graph. End behavior comes from my leading term. Odd, so the ends go in opposite directions. Positive, so overall it's increasing, which means I'm going to start low, finish high for my end behavior. I need to graph this, which means I'm going to need to find a root. How many roots do I have to find using synthetic division? Well, it's 3rd degree, so if I find 1 root using synthetic division, my quotient will be squared. Remember when we were doing that division, every time, whatever my degree was, I divide out 1, so the quotient gives me 1 less as the degree for the quotient. So if I find 1 root using synthetic division, then my remaining quotient is squared, and I can just factor that out. So if it's cubed, 3rd degree, I only have to find 1 root using synthetic division. Well, where do I start? Right now, we're going to start with what we're given. We are given that 2 is a root of our function. So if I want to think about my 0 multiplicity behavior chart, I know that 2 is going to be one of my zeros. It's going to be one of my roots, because I was told that here, which means I'm going to do synthetic division by 2 to find what I have left. I don't need to worry about 0 placeholders. Work through my process, bring that down, multiply on the outside, and add on the inside. Remainder is 0, so I found a factor just like I was expecting to. Now we need to finish factoring it. So this root 2 gives me the factor x minus 2. And then my quotient here is 2x squared minus x minus 1. And I can finish factoring that. That'll have to be a 2x times x. Negative 1, that's going to be 1 and 1. 1 is going to be plus, 1 is negative. I need a negative x in the middle. So I want to make whatever's multiplied by this 2 a negative 1 and then a positive 1. So that's a negative 2x, a positive 1x, negative 2 plus 1 is a negative 1 in the middle. So here we go. There is my function completely factored. I think about setting each of those factors equal to 0 to find my roots. I've already got this one right there. This one's easy. If I set that equal to 0, I get 1. I need to maybe do this a little work. X plus 1 equals 0 to figure out 2x minus 1. Divide both sides by 2, and I get a root of a negative 1/2. The multiplicity on each of these factors is 1, which is an odd number, so I'm going to cross the x-axis at each of those values. Okay, let's come over here and number our graph. We have positive 2 as one of our x-intercepts. We have positive 1, and we have a negative 1/2. There's our 3 x-intercepts. Don't forget we have a y-intercept. So let's go ahead and get that y-intercept graphed. We have in behavior, so I know where to start and where to finish. I'm going to start low, go up and hit that y-intercept, cross at each of those, and finish going high. What do I know and not know? I know I've got a hill here. Don't know how high. Don't care right now. I know I've got a valley here. Don't know how low. Don't care right now. This is a relative maximum. It's a hill. This is a relative minimum. It's a valley. That means I have 2 turns, which is legal according to the degree of my polynomial. All right, we have got it all put together. We know how to solve and sketch our graphs for polynomial functions. I do want you to remember that we will not be using graphing calculators. And if you try to plug this into a graphing calculator, these usually go really high, really low, and what you get is just a series of lines, it looks like. So I'm going to know. You're not going to have graphing calculators, graphing utilities on your test, so using those for your homework doesn't really help at all. It might be able to back up your graph if you are good at setting the windows, but just keep in mind that that's not usually a helpful thing.